from now on you're being recorded. Just making this official disclaimer. Okay, so let's dive right in. So I hope things are going well in principle. I am today only on one screen. I'm traveling right now, so this is all a little bit more complicated right now. Hi, Rishab. Okay, so we will be talking. So how are things going? Have you had time? So I hope, Manvit, you were able to open the book now. And,
yes, Professor. I was able to download it.
Excellent, excellent. Okay, glad we have this sorted out. Rishab, were you able to access the book?
Yes, Professor. Yeah,
okay,
I was able to access the book.
Fabulous. Okay, good. Okay, so how are things? Have you had time to look into the final project and the data files that I have provided in that regard? So have you dedicated some time to maybe look about what hypothesis you may be interested to pursue? So I see a lot of benefit that you would start early with that, because it will require quite a lot of thought work that needs to go into that, and I think it made sense to get a head start to kind of start thinking about it quite early in the semester. So I really suggest that, because it will require a little bit of research on how to approach things. Okay, I hope you all enjoyed the discussion boards, the video that was posted. I hope that was interesting. And
yeah,
you commented. Glad to hear that. Good. And so we're going to continue today with descriptive statistics and graphical displays. So, okay, so I can, okay. Okay, so I have the video now. Okay, okay. So let's dive right in. Let's get started, because I want to spend a little bit more on the lab today. We have a little bit more to cover today. Good. Okay, so we're back today with descriptive statistics and graphical displays. And we briefly talked about the mainstays of statistics and the importance of the various tasks of statistics. And it's really descriptive statistics is really the basis of everything. And we have briefly talked about it already in last class. So there are different variable types, and there are different ways to look at data. And it's super important to understand the nature of your data. How is your data structured? How does it look like? And how does it distribute? And we will have a separate lecture, I believe, which is the next lecture that is to come, that will talk about the frequency distribution and how data actually distributes and how it looks like, and how you would approach different distributions. So today it's really about how to describe data, how to display data, and how to display the distribution of data. And it's really, it's the mainstay, and it's the basis of what we will be discussing later as when we look into the different frequency distribution. Okay, so descriptive statistics is really the basis of everything, and it serves as the basis for inferential statistics, which is essentially the next step. So what we're going to be covering today is, so we will have a quick review of Module 1 and what we discussed in the context of Module 1. We will be discussing frequency tables, which we have briefly touched upon already in Module 1. We will talk about bar plots, histograms, box plots, and dot plots, which are all elegant graphical solutions, how to display and how to look at distributions. Then we will talk about ways to measure the center. We will look into mean, median, and mode. And then secondly, we will be also looking at how to measure spread being the variability in your data, right? If you can imagine, we talked about the single observation, and these single observations, they will have some center around which they're distributing, and they will also have some certain kind of variability around that center. And this is what we will be talking about today. So a lot of what you hear today, you may have heard already in earlier times of your education, and it may just be a little bit of a recap and maybe redundant, maybe not that interesting, but I think it's just important to kind of start the course essentially by talking about these simple terms and repeating those simple terms. Okay, so let's continue. So we have spoken last time about populations. A population as an entire group of interest and a sample as a subset of this population to essentially describe the distribution, the center and the spread, as well as dynamics of the overall population. So essentially you're using the sample to find out what dynamics you likely also see in the overall population. You do that by looking at individual records or observations, which essentially is data of one individual. That can be true, doesn't always have to be true. It really depends on that level you're looking at the data. So usually you look at the level of a patient or a subject, or in many cases, you also can look at it on a visit level. So you literally would say, I look at this data at the level of a treatment, an office visit, at whatever metric or time metric or individual metric you actually want to look at. So in my world, for example, in the dialysis world, we look at it from a lot from the treatment level perspective. Reason for that is because we have patients that come in 156 times a year. So we literally have data for each dialysis treatment, and to get actually from a treatment level to an individual level, you would need to have some form of aggregation already to essentially look at aggregated values over certain defined time periods. So, so it's really record or observation. It doesn't always have to be an individual, but it's an individual entry. And that can be an individual visit, an individual treatment, or individual patients or subject. Good. So the tasks of descriptive statistics are really summarization and visualization of data. And inferential statistic is really learning about the population from the sample. Mainly essentially dynamics or comparisons from within samples and to extrapolate this to the overall population. So then we have variables, and the variables is basically a characteristic that is recorded for subjects in a study. Notably, these subjects are mostly from samples, and they can, in larger scale, hypothetically, they could be from a population, but populations are just hard to quantify and to collect over an entire population. So usually you look into study subjects or sample subjects. So now we have three main kinds of variables. We have nominal variables, which can be binary or categorically. So there we have, for example, treatment group. So that can be one treatment group, two treatment groups, three. It can be several groups. Then it can also be only binary, which, as the name implies, essentially has only two possible values. So it's usually, you would code it. So in R, you would code it as either a 0 or a 1. In SAS, for example, as in SAS and SPSS, for example, we would code it as either a 1 or a 2. I personally find 0 and 1 just super intuitive. Also, and we will see that once we come to the respective topics, also because arithmetically it just makes a difference, right? So if you include, and I don't want to go too deep into that, but if you include a binary variable as a 0 and a 1, you essentially have in, let's say, an equation where you include this variable as an average value, you essentially have 0 as this being not represented, whereas a 1 is, it is presented arithmetically. So that doesn't make too much sense at this point, but just flag this as a bit of a background information, and we will revisit this one once we come to the arithmetics of the models we will be looking at. It's just it making a difference arithmetically, and I think it's easier to grasp than coding it as 1 and 2, like SPSS or SASTAs, which I always found a little bit confusing, to be honest. So we have ordinal variables are essentially variables that do have an order. So we have an order amongst siblings that essentially follow a ranking. Then we have data that is sometimes nominal and ordinal lumped as categorically. We have quantitative, either discrete or continuous data, which can be the number of children, which is a typical discrete count, whereas height, weight, and age will be a continuous variable that essentially distributes continuously. And this is usually where data
Professor?
ऋषभ,
Yes.
आवाज आ रही है?
Yeah, I can hear you.
You can hear me? Like, is Professor's connection's gone, I guess.
Yeah, I guess. David, you are able to hear us?
Yes, I can hear you. I think
Yeah, he left the meeting.
we should close the meeting and start again, or I don't know.
I know he'll drop some message. Let's wait. We should stop the recording, I guess. Mike, Professor Mike.
Yes, can you hear me?
Yeah, now
Yes.
we can hear you.
Yes, sorry, that was my internet. I have a little bit of an unstable internet right now. Okay, my apologies for that. That is rather what should not happen. When did I lose you? Where did we stop? Okay, so we're now on my phone, so that should be better. Okay, so did you hear the variables?
Yeah,
Now
yeah,
you're
we
mute. Yes. So it happened right here, right? When we talked
Yeah,
about
it was
frequency plots.
ordinal and binary. Sorry, I was on mute. It's ordinal and binary where we left off.
Okay. Okay.
And Professor, can you resume the recording?
Yes, it's recording. I just made sure. So we are recording. Okay, so my apologies for this hiccup. So that was rather unwanted. What happens occasionally? What can I do? Sorry. Okay, so we are now on my phone, so this should be considerably stable. This shouldn't be an issue. Okay, so we have nominal, ordinal data. So we have binary data where we actually have here this distribution between two binary data, which is treatment or control. In this context, you would usually set treatment as a 1, whereas you would set the control as a 0. So this is the typical way of how you would code it. For that reason, because it is an additional feature, it is an intervention that basically weighs in every probabilistic model you would develop as a 1, and this would basically have a weight as an intervention. So from that reason, you would treatment or quote unquote intervention would be counted as a 1 if you would be coding it. I think that is fairly established. I think you would not find many statisticians who would do it differently. Then you have the ordinal data summaries, you have frequency table, you have here ordinal variables, you have mild, moderate, severe. Essentially, a characteristic is a nominal variable that essentially has some order that is being displayed in it conceptually. So essentially, we have treatment and control. We have here mild, moderate, and severe, and you remember from last time, we actually then combined this into a contingency table where we had two groups, treatment and control, and we had these 50 individuals in the treatment group and these 50 in the control, then further substratified into pain category, mild, moderate, or severe. And by that, you can use your descriptive statistics to also conduct already some form of inference. And this is what we will be doing with the chi-squared test, which will be the only non-parametric statistics that we'll be discussing. Good. Okay, so this is the comparison. Then we have pie charts as an alternative to depict data, nominal data, and the distribution amongst participants. And this is a good example, essentially, why pie charts are actually a rather suboptimal way of depicting data, because just by looking at this pie, you cannot really say whether this is really a useful kind of quantification of that percentage, of that proportion that actually was eaten. So the pie I have eaten versus the pie I have not eaten. It doesn't really give you a clear idea what that proportion actually is. It's somewhere between 25 and between 25 and 50%, you know that. It's probably closer to 25% than it is to 37.5 as the middle of between 25 and 75. So, but it's a very inaccurate, imprecise measure. So from that end, pie charts are just really not a good way to show. Bar charts are just much more precise in depicting proportions and definitely preferable. So a bar chart would look here like it is shown right here below. So that would be the just much neater way to depict your data. So, okay. So then we can basically show data also numerically as either frequencies, proportions, or relative frequency, or percentages. So if we have 40 students and only 4 students received an A, we have a frequency, which is 4 out of these 40 students have received over the period of 1 semester an A. A characteristic of frequency, and this should always prompt you to think of a frequency, is the incorporation of a time. So whenever you have a time metric, most likely you're looking at frequency. Whereas proportions or relative frequencies are essentially only giving you a proportion. So it's 4 out of 40, which is essentially 0.10. Multiplying that by 100 gets you to a percentage. But at this point, this is really, it's just a formality to multiply it by 100. Some people prefer percentages over proportion. I personally do enjoy proportions quite a bit. And I would, most cases, I probably would prefer proportions over percentages, but it depends on the context, right? Whenever it's about probabilities, for example, I would always go for a proportion. I would not go for percentages. But what's most important at this point in time, any of these can be used for frequency table or bar plot. Good. Then we have graphical summaries, and we will talk about this today. We have dot plots, where basically each observation is a dot or a dash. Then we have histograms, which is a categorization of data, then basically is showing this data as a bar plot. And then we have qualitative and quantitative measures that basically go together in a box plot, which you will see is a very neat way of depicting data. And all these plots help to identify central tendency, spread, skew, and outliers. And we'll talk about this today, what that actually all is. So essentially dot plots and histograms. So it's really, it's nicely shown here on the side between those two, 3 graphical ways of depicting data. So the dot plot really has the highest granularity. So it gives the highest insights in terms of detail into the data, whereas box plots are really aggregating already to an extent that you can't really see individual observations anymore, except for those extreme outliers, which we'll discuss in a second. So it's really more detail is a dot plot, less detail is box plot. So it really depends on the question at hand, which one you would choose. So here is the dot plot. So here we have individual observations. So each point here would be one observation. You definitely can do some quote unquote binning. Binning essentially is where you define certain smaller ranges that contain the respective observation. So here the binning that you would assume here to be done is basically that from this outer rim to that rim, that would be one bin. Whereas an histogram, for example, usually has larger bins. So while you have here the observation, here in the histogram, you have the frequency or the count within that bin. So you have here, let's say 100 to 100, okay, that's 50 divided by 3, that's like 16. Between here, 100 and 116.6, you have like 3 observations. So you count how many observations fall into this range. And by that, essentially, you get a distribution, and this is your frequency distribution, right? By definition, this is your frequency distribution. And now, if you change the bin size, you will get different levels of insights because the count is changing, right? So if you make a wider bin and you extend the bin, obviously you will have a higher count in there. It makes a lot of sense, right? So if you are here extending the bin to from 100 to 125, you're actually capturing 8 entries, which are here. These 8 entries that you have seen here, 2, 2, and here 4. So this is 2 and 2 is 4 plus 4 is 8. So these are your 8. So you essentially by that, you basically capture more of your data. So the bin size will affect your count. And by that will affect the shape of the distribution, and it will shape how the data presents itself to you. So, any questions so far? It's quite intuitive. It's considerably simple, right? So then we have histograms as really being a very elegant way to depict your data, to show your data, and to further also allow for you to understand how does your data look like, and what is the center of your data, what's the spread of your data, and how does it shape. So a distribution is centered by finding the median, and as the median, you really define that threshold below which and above which you will find each 50% of your data. So this is the exact center of your data. And that is a very powerful insight to know that, and we'll see why. Then secondly, we also have the spread of a distribution. So the spread essentially means how far does it distribute out. So if you have a continuous variable, your data can spread quite a bit, right? If you I don't know, measure a parameter like, I don't know, the weight on a spreadsheet, on a cruise ship, or I don't know, like cargo ships, cargo containers, whatever, which has a large numerical value, this will spread quite a bit. And then you have physiological parameters which spread less, but they still spread because they also have a certain kind of spread in its data. So the spread is always to some extent dependent on the variable per se, on the range of possible values, and on the actual variability and why there is variability. And this variability research is actually quite an interesting kind of conversation topic by its own right. So further, you will also look into the shape of a distribution. So you will look at shapes and you will judge whether this is roughly symmetric, whether this is really a nice normal distribution that actually really has the classically symmetric distribution that you would expect for a normal distribution, was quote unquote the bell-shaped symmetric curve, or the data is skewed to the right or skewed to the left. And what does this mean? So essentially we have the skew. So as we have spoken about the skew, so we have symmetric distributions and a normal distribution. Symmetric distribution means there is one mode, so there's one peak, one highest point, the point of highest, the value with the highest occurrence. This is this point, this is this mode. And left and right of this mode, you have the bell shaping, and then you have the tails on the side extending further in the realm of those outliers, those extreme values. So the symmetric distributions are really left and right of the histogram, and it's really meant to be a mirror image, so to say. So if we are talking about skewed data that is skewed to the left, we're basically talking about the distribution that is skewed to the left when the left tail is longer than the right tail. And analogous and in the same sense, skewed to the right means that the distribution that is skewed to the right tail is longer than the left tail. So what are examples for skewness, and what do you find? You will always find a kind of very typical representation for a left skew when you think of lifespan, for example. And this is just one example. So there are a million examples, right? But essentially, when you think of lifespan, you know that the age pyramid is shifting nowadays. So over the last 50 years, the age pyramid has substantially shifted, with people getting older and having less children, which means from that end, the age pyramid is already shifting very much to the left and is skewing to the left. So, but now you even have with lifespan, it's more likely with modern medicine you get older. So people are basically older to some extent, but then you have some that also die younger. So essentially, this is a typically shape and form of lifespan data. Whereas if you want to look for, and here you have left skewed data, because the skew and the tail is actually longer to the left. So you would speak of that in terms of a left skewed distribution. Whereas when you want to look at right skewed distribution, you have here a distribution. Majority of people will have some income around a certain center, but only a smaller fraction will have a high income that basically leads the skew to the right. So this actually is a right skewed distribution. So then the modality. So we have now, are there any questions to the skews? So I really flagged this because there will be a lot of tricky questions on the quizzes that will actually ask you for an understanding of exactly that. So if there are any questions, I think it's a good conversation topic to have, and maybe to think twice about it. But it's considerably intuitive. It's really not that complicated, I find. Any questions? Otherwise, let's move on to modality. And with modality, we really have essentially only one thing to observe, which is really this point of highest occurrence. So the value with the highest occurrence will determine the so-called mode. And here it's quite obvious. Here's 100 as the value with the highest occurrence. And this is basically the center of the distribution. Then we have unimodal, would be that distribution we're seeing here, where we basically have one mode only, and all the values are basically distributing around that one mode. Then we have two modes that would essentially be labeled a bimodal distribution. And we're basically seeing two modes to areas with highest occurrence. So this is the modality of the distribution. And so now in the context of skewness, we also briefly touched on outliers. So essentially what you see with tails that extend to some extent longer in one direction than actually in the other direction. So this is caused by outliers. And these outliers fall essentially far from the rest of the data. And so once you see here, for example, you see this outlier that is here far out. So this will lead to a tail extending further to the right than on the left, and will lead to a longer tail to the right. So this will be a right-tailed, right-skewed distribution. And what I really just want to say briefly about outliers, so outliers are always problematic, right? So when you think of data, you have like this beautiful data set that you try to make sense out of your data, and you try to conduct inferential statistics, and you're trying to understand what essentially your data tells you. And then you have like 5 out of your 1,000 patients, you have like 5 terrible outliers. They're absolutely terrible, and they don't fit into a picture, and they basically they avoid your data being significant, the comparison you're doing, or the logistic regression model that you're building is not significant because of these few outliers. And they're just so extreme, and they're pointing in the opposite direction, and they make your data a little bit too unreliable in some certain regions of magnitude. So now, how can you remove outliers? So the argument could be just let's exclude them, right? Now, obviously, you can't do that. You need a very strong reason to exclude outliers. So if you exclude outliers, and you wouldn't disclose this very transparently in your publication, which you're trying to get published, and you would very much shed doubt on your scientific integrity. So it really makes a difference how you deal with outliers, how you deal with data, and how careful you actually deal with your data curation, like from the beginning, from collection to management, database management, as well as then data cleaning. And the quote unquote data cleaning is usually what is most important. And so, as you can imagine, if you have a very large database, you will have a lot of outliers just for documentation errors, or just for errors, measurement errors, errors of data transfer error. Back in the days when the manually entered data was even worse. It's like, thankfully, that is not done that frequent anymore. It's still done. Still a lot of data is manually entered, but most of the data is nowadays not. And this is actually really good, because that kind of takes this human component out of data collection. But it used to be an even greater problem than it is right now, but it still remains a problem. You still have outliers that are caused for avoidable reasons, but then others you have for non-avoidable reasons that you just don't know. And particularly in epidemiological and retrospective studies, you will just not be able to essentially go back and find out what's going on. So if you have data that is not possible, and which is just absolutely not acceptable in what physiological knowledge you have, like somebody reporting a heart rate of 20, right? Like no individual could live with a heart rate of 20, or a heart rate of 250. It's like the maximal heart rate is 220. So those of you that maybe those are athletically inclined, is usually the maximal heart rate of that you would assume for your age is essentially 220 minus your age. So if let's say if you're 30 years old, 220 minus 30 would get you to 190. So that's your maximal heart rate. And then you try to estimate, for example, aerobic versus anaerobic thresholds and zones. So I'm a runner. I'm currently training for the marathon in New York. So I'm dealing a lot with that, and I read a lot about these things. So you basically have this aerobic versus anaerobic zones, and you assume this to be in reference to your maximal heart rate, and the maximal heart rate is 220 minus your age. So from that end, so if there's something that is so low or so high that is just not possible, this is an outlier that you can remove, and that's perfectly justifiable. But you need really good reasons. And long story short, this is essentially what you need to keep in mind. You need a good reason to remove outliers. And you need to transparently disclose these outliers and this outlier removal. And you need to disclose the reasons. So yeah, so these are outliers. So this is really, there are even books written about outliers. So very important to keep in mind. So don't just remove them. So then we have box plots. So we talked now about dot plots, histogram, and now we're talking about box plots. So box plots are those with the most aggregated kind of perspective to look at your data and with the lowest level of detail and granularity. Is it necessarily a useful way of looking at data? Yeah, I think it is. I think it is. I wouldn't intuitively do it, but I would do it. Let's put it that way. I would do it probably more for a group comparison, but then definitely favor box plots or so-called violin plots that basically show you the distribution right over the entire range of your box plot. And we can look at a picture of a violin plot in a bit. So essentially, you get some idea about the shape and distribution of your distribution, of the way your distribution looks like when you have a box plot. And why? Because you know what the box plot shows. So you have the quartile is the 25th, 50th, and 75th percentile. So now what does that mean? So we have here again the pain severity. And this was essentially, the pain severity was defined based on its distribution. So if we have here the so-called Q1, that's basically the 25th percentile. So everything to the left of Q1, so from that value, which constitutes Q1, towards 0 is your 25th, is the 25th, the lower 25th or the lower quartile of your data. So the highest level in your lowest quartile is the 25th percentile or Q1. If you have Q2, that's your median. Below the Q2 or below the median, you have 50% of your data. And above the Q2, you have again 50% of your data. So then Q3 analogously is your 75th percentile, meaning that 25% of your data is greater than this value, whereas 75 is smaller. And lastly, as our first measure of spread, we have here the IQR, the interquartile range, which is the spread from the 25th to the 75th percentile. So this is the middle 50% of your data. And then we have the whiskers, and the whiskers are essentially Q3 or Q1 in that direction, plus 1.5 times the IQR. This is the spread. So, and what's very characteristic, so every data point that is not within the whiskers will be shown as an actual outlier. And this is already where we're coming to one way of removing outliers. It's like, so I have seen approaches where people have removed outliers that did not fit into this criterion. And it's not a wrong kind of approach. So, but it's a definition question, right? You need to be sure that you're not changing your data to an extent that will have will backfire to some extent. So fact is also that box plots do not display the shape of your distribution as clearly as histograms because you're missing this detail, this granularity. Yes, is there a question? Yes.
Yes. Can you clarify again what the line is representing the Q3 plus 1.5 IQR, what that indicates.
Yes, so this is a numerical value. So if we have here the severity, let's say here the median is 50, which is this line here, then you have Q3, that's this line here, so that's somewhere like 50, 55 or so. And then you have with the whiskers, you basically have Q3, so this is this numerical value, so 55 plus 1.5 times the IQR. So if we're assuming here the IQR is from 45, this is more like 42. Let's say it's from 42 to 57, and let's make it 15 for the sake of it being a little bit easier to calculate. So we have Q3 at, actually not that easy to calculate, but 57 plus 15 multiplied by 1.5, which would be 22.5, would be your IQR. So that would be 57 plus 22.5 would be 77, 79.5. So this would be 79.5. It's not really an accurate estimate. Does it make sense? So we have here the median at 50. We have the Q3 at 57. And then we have IQR is 42 to 57 is 15. And 57 plus 15 plus 15 multiplied by 1.5, this is 22.5. So 57 plus 22.5 is 79.5. Does that make sense? So it's a definition question.
Is that the threshold beyond which we say something is an outlier? Is that what that means?
No, you cannot say that with certainty. Again, outlier is a definition question, right?
What's the significance of that number, of that numerical value?
None. It's a definition for a box whisker plot. I don't know of any reason why that is. I think it's just it's a considerably conservative estimate, which they have chosen to kind of not depict too many outliers, but also not too little outliers. So I don't, and actually I'll try to find out whether there's something. I'll get back to you, but I don't think there's a particular reason why it was chosen that way. I think it's just a definition of a box whisker. Does that answer your question? Yeah?
Yes,
sure.
Thanks.
Sure. Okay. So box plots, so we looked at box plots for single distributions and how, and here we're looking for box plots for comparing distributions. And again, they're useful to identify outliers or to look at outliers, and they are super useful to make graphical comparisons of two or more distributions. So this is what I meant before. So I would not necessarily show box plots for a single distribution. I would use them to depict two distributions and to compare two distributions. I think for that they're much more useful. Essentially, I've not seen many where you just do one and one distribution. But yeah, for the comparison, I think it's super useful graphic depiction. All right. Any more questions about graphic displays of distribution? If not, then I would say we're moving forward now to numerical summaries. And this is where we're coming to mean, median, and mode, quartiles, percentiles, which we have touched upon already, range, and the standard deviation. And I don't want to be too long because I want to get to the lab. So we have with the mean, and you all know the mean, right? This is the regular arithmetic mean. So it's essentially the sum of the observations divided by the number of the observations. So basically we have I equals 1 to n, or to I equals n. We're summing that up of each individual xi, each individual observation, and we're dividing that by the n. This gives us the x bar, the sample mean. So the mean is not resistant. It's strongly influenced by outlying values. So as soon as you have outliers, like here, for example, in log normal distribution and exponential distribution, it will strongly be affected, much stronger than here. And since this is a box whisker plot, you see already how strong this is affected. So if there's a positive skew, a right skew, So if you turn this around, that would be a right skew. If you have a right skew, the mean is pulled upwards, which you see here, whereas the median remains rock stable. So this is important to keep in mind. So you can, based on the relationship between mean and medians, you can also kind of draw conclusions about the distribution per se. So you will know whether the data is skewed or not. If you have data that is skewed to the right, the mean will be more positive than the median. And that is already how you can say, okay, so I have a right skewed observation. So if you have both mean and median, you don't even need a histogram. You know already what the skewness is. So median is the midpoint of the observations. We talked about that. If the number of observations is odd, meaning that you have an odd number where you have 1 in the middle, then the median is that middle observation. If you have an even number, then you need, then it's a little trickier, but then you need the average of the 2 middle observations, which is then how you approach that. And the median is really the 50th percentile. So the median is the midpoint of the observations when they're ordered from the smallest to the largest, or from the largest to the smallest. The 50th percentile, second quartile. So what really makes the median a very, very useful and very powerful mark of the central tendency and the reflection of the center is that it's really absolute resistance against the outliers. So you have 1 and 2, 3, 4, 5, 3 is your median. Whereas when you have 1, 2, 3, 4, and 1 billion, you essentially still have 3 as your median. So now imagine this would be an average where you sum all of this up. Your mean has just shifted somewhere in the realm of like 10 million rather than being 3. So if you have an even number, your median would be 2 and 3 divided by 2. So it's 2.5. This is the even setting. And yeah, so you have the median height of the 7th fourths. So the median fourth is in the middle. If you have a basketball team, median fourth is still in the middle, although it's not a fourth. So it would still be the same thing, right? And yeah, then we talked about the mode. The mode is the most often occurring value. It's often used with categorical data, and it's the highest bar in a histogram or a bar chart. And the mode changes with the width of the bins. Central tendency and skewness, as said, you can infer your skewness from your data. So when you have outliers and you have a right skew in your data, you essentially have the mean being pulled the most to the right. The median, well, if you have a lot of outliers, it will pull it to the right as well. It will also pull it to the middle. But the mode will always be the same. And that is also true for left skewed distribution. Makes sense, right? And please really keep this slide in mind. It's a very important slide. So the percentile is a value such that P% of the observation fall below or at that value. So this is really a threshold below which you have XYZ percent of your data, or XYZ percent of your data above the threshold if you do the inverse of that percentile. But yeah, the definition is it's the percentile that is below that threshold. Quartiles. Quartiles split the data into 4 equal parts. So you have the median is the second quartile, Q2, 50% of observations are below, 50% are above Q2. First quartile is the median of the lower half of the observations, 25% of observations are below Q1. So you have Q1, the quartile 1, you have quartile 2, quartile 3, and quartile 4. So this is essentially a way of also categorizing the normal distribution. The range is the simplest of all markers of the spread. And this is already where we're really getting very much into the spread per se. So the range is really just the max minus the min. So you have the maximal entry and you subtract the minimal entry, you're getting to the range. But now most commonly used. So the range is actually something you don't necessarily see often, but you will always see a standard deviation. And the standard deviation is really only a useful way of depicting spread in the normal distribution. So essentially what you would do if you have skewed data, strongly skewed data, you would not use a mean and you would not use standard deviation because both are very much influenced and are not resistant against skewness. So you will only use mean and standard deviation with normal distribution, and you will literally show mean plus minus, and there's a plus minus sign that you will find in Excel as well as in Word. So mean plus minus standard deviation, that's the way how you show it in scientific notation. If you want to show skewed non-parametric data, you basically would show median and the 25th and 75th percentile, or the IQR alternatively. So you rather resort to these reflections of center and spread for non-parametric data, whereas parametric data you can nicely show with mean and standard deviations. And when essentially looking at mean and standard deviations, you have one step in between. You basically have the so-called variance. So the variance essentially is, so you will measure, and this is shown here. So you have X bar, which is the mean. You have XI, which is the individual entry. So let's say you have like 100 patients and you're calculating 100 individual entries minus your average of all these 100, you get 100 differences. These are the so-called deviations. Squaring this gets you to squared deviations. Adding and summing up all these individual squared deviations gets you to the so-called sum of squares. So this is what we're looking at here. So this is from I equals 1 to I equals n. So this sum of squares essentially, if you divide this by either n minus 1 or n, depending whether you're looking at the sample or you're looking at a population or a set statistic or t statistic, you get to an average squared deviation, which is, so your squared deviations, you sum up your sum of squares, you sum the squared deviations, you divide it by your sample size or degree of freedom, like here with n minus 1, you get to the variance. And the square root of the variance is your standard deviation. This is to be seen here. So again, so this is extremely not resistant to outliers. So as soon as you have a different distribution, you will get inflated standard deviations. But it's definitely, it's a very convenient, it's nevertheless a very convenient marker to describe normal distributions. So standard deviations has the same units as the observed variable. It measures the spread of the data. It is a standard deviation of 0 only when all observations of the same value, otherwise the standard deviation is greater than 0. As the spread of the data increases, standard deviation gets larger, which makes sense because you get larger deviations that are then even being further accentuated by squaring them. Then you divide them through the sample size or the degrees of freedom, you get an average. But again, this is influenced by your size and magnitude of the deviations. So it's not resistant, and therefore you would not use it for skewed data. Good. Same story, you would see this kind of reflected here when you compare here the standard deviation. You see the strongly skewed data here, the log normal distribution. You see a lot of outliers, right? Look at the standard deviation. The lower bound of the standard deviation is not even on this graph anymore. That has disappeared from the graph because it's so much negative. And these usually cannot really be negative, but they're just arithmetically, they will become negative. So they're not even displayed here anymore. So this is really what's meant by it's not being resistant. Yeah, then some more exotic well, the IQR we talked about. So this is considerably robust against outliers. Then here, range also quite robust, but not fully robust. Most robust here, the median absolute deviation. So this is a more exotic kind of reflection of the spread. I personally have never computed it, but it is one possible way to reflect, to calculate spread. And definitely keep it in mind, but it may be not what reviewers would be very happy to see. So maybe kind of consider whether you're not better advised to kind of resort to more traditional and conservative measures of spread. Up to you. So this is basically what we discussed. Make sure to review mean, median, mode to understand the dynamics, understand the graphic displays, understand what a mode is, unimodal, bimodal distribution, and understand skewness. That's important. And know and all right. Any questions? Or was that all here? I think it's easy, right? It's considerably intuitive to some extent. It's just really important to kind of review it and kind of make sure that we're all on the same page. Any questions? If not, then we can move on to the lab. So we have half an hour for the lab, which is nice. Good time frame. So please open your R. And let's get started right away. So I hope you all have seen Practice Lab has posted now. So you can now, when you open your R, please open a new script and save it right away. Save it into our folder on the desktop. And BTM600 Module 2, and this is now Practice Lab 1.r. Okay. So now we have our first R script. Good. So again, so we have now. Okay, let me minimize this. Make this disappear. In case of questions, please speak up. I can hear you. I've minimized you, so I don't really see when you. I'm today only on one screen, so it's a little harder.
Professor,
So please go on Canvas and please copy. Could I what?
What to do? Like I've opened R next. I have to open the Practice Lab 1.
Yes. So on you see on the canvas, you see in the modules. You see Practice Lab, not module 4. Now here you see Practice Lab, and if you go on Practice Lab, you see here Practice Lab Module 2. You can now download the code. Yes. And by doing this, you basically you have this. You can load this automatically in your data, you see. So you get Arbuthnot and you get present. Yeah. Did that work for everybody? You alternatively, if there are problems, I also put the data in the actual module. So you can also download it directly from the module. Oh, yeah. So here you have Arbuthnot that's present. So I hope this worked now for everybody.
No.
Yeah, no?
It hasn't worked for me, to be honest.
Okay, let's try again. Which part did you try? Did you copy paste?
I opened I copied it. I opened the R. I opened new script, and after that, I've pasted it, but it's not showing any values already.
Okay.
Yeah,
So
it's
did
the
you
same.
copy it? Yeah. So did you copy it in here? Do you have these 2 lines in your script?
No.
Oh. So if you just go with your cursor, so copy it on line 1 and line 2. Go on line 1 and click Control and Enter. This should open automatically these two files that you see here on the right. Did that happen?
Well, Professor, it's not working somehow.
No, but I see it on the Canvas page. I wasn't able to paste this link and have the data come up, but I found it on the Canvas page.
Yes, it's on Canvas, right? So you have Practice Lab. You go on Practice Lab. You copy this line. Then you go into R, and you copy paste it in there. Did you do that? Did that work? Let me drop these lines in the chat. Maybe this another problem. I don't know. Does this work? If you copy paste this in a script,
Professor, you continue. There was some issue with my software right now.
okay. So there's a different problem. Itzar, are you able to do it?
Yeah, I'm doing it. Some issue with my software right now. It's got rehanged or something. I don't know. I'm reinstalling it. Will take time. I'm listening to timing.
Okay, sounds good. Okay, so let's try to carry on. Stay on afterwards if you have problem on it. Okay. Okay. Everybody else has this data now loaded as an object in R. So if you want to extract now just the number of girls that were baptized in that year, so Dr. Arbuthnot did his calculations in the 17th century. So you have now a data set that is called Arbuthnot, right? So you see here that you have here time series data. You have year, boys, and girls. So if you, and you know this already from DataCamp, right? So if you go Arbuthnot year, you get a list of the years. So these are all the years that are in there. So this starts with 1629 up to 1710. If you do Arbuthnot girls or boys, you address only boys and girls. Yeah. So these are your numbers. So when the question is, what command would you use to extract just the counts of girls baptized? This is the way to do it. So this is essentially how you extract the counts for the girls that were baptized. And then you can do summary statistics of these variables. You can do summary. Then you can also find out which year. So these are your summary statistics. So this is your mean, that's your median, that's the first quartile, the third quartile, the max and min. So these are basically the entries. So if you want to, so let's do some simple programming. You know how you can basically address every cell in your data file. So if you want to do Arbuthnot and you want Arbuthnot and you want that entry where Arbuthnot girls was consistent with the maximum value for Arbuthnot girls, you would basically do this and then you need a comma. So you're doing this here by using this double equal sign. You remember? By that, you assign the following. So you say arbuthnot, I want the entire data frame arbuthnot. So I want all the columns, but only for that row. You remember everything before the comma is a criterion for the row. Everything after the comma is a criterion for the column. So you leave column blank. By that, you get all the columns. You take this before the comma, which is basically all the girls, and you take that row where the girls entry is equal to the maximal entry of arbuthnot girls, because the maximal entry here is 7,797. No, 79, sorry. It's been a long day. So here the maximal entry, is exactly the same, right? It has to be. So we're assigning this and we're saying, okay, so we want only that entry. This is entry 77 in year 1705, where we had 8,366 boys, or 7,779 girls. So if we want to do the same thing now with the minimal entry, we can do this the same way. We just need to change the max with min. Yeah? And now it's 1650. There were generally less boys and girls born for some reason. Hard to say why, but could be a lot of things. It could be, for example, that childhood mortality, infant mortality was high, and children just didn't get to the point that they were actually baptized. That's a possible explanation. Another explanation was were just less people. Like maybe there wasn't, I don't know, maybe there was a war and there were just not that many births. Men had to fight the war and went home, and there were many childbirths. You don't know. So there are manifold reasons why that could be the case. But it's interesting to kind of approach the data from that perspective. And this is already where you draw inferences, right? You do your descriptive statistics and you draw inferences. So now we're displaying stuff. So how are we displaying stuff? So you want to display this with something that is called a time series. So you can do a time series, you can show its plot. So you do arbuthnot boys as a function of, let's actually do, okay, so you have two ways. So either you can do as a function of, but forget that for now, let's do arbuthnot. So you do x-axis first. So you do arbuthnot year, then arbuthnot boys. And that's what you see. That is the dynamic you're going to be presented with. So this is the dynamic of boys over time. And this is our lowest, this is the nadir of birth, right? So there must have something happened. There must have been some war or something, or some famine. I don't know. Everything is possible. So you can do the same plot, obviously, with girls. The same story, right? It's the same depiction. Good. Okay. Same story. So now you have the girls plotted. No? Oh, yeah, here are the girls. So these are the girls. So now you can work a little bit on the aesthetics of that graph. You can essentially what you can also do, you can do points. You change plots to points, and by that you can show the girls on the same graph. So you can do col equals red. So now you have the girls in red, whereas the boys are still in black. If you do this, you get this. So now you have boys and girls on the same plot. Nice, no? Nice graph. So what else can you do? Then you can change. You can do boys. You can say xlab. Xlab is basically a function how you say is, and on the x-axis you say birth. So that's y lab. Oh, and now the y-axis is a birth, and y lab is this birth. Birth is boys in black, girls in red. You usually would do this with a obviously with a legend, but I'm not gonna. I spare you the legend for today. Okay, so plot points. What else? Boys, black, girls, red. Okay. Okay, so this is this. What else do we want to do? We want to display now girls point all children. How can we do all children? Okay, so that's a little bit trickier, right? So now we want to do all children. All children would be, for example, do this. We could do birth total. Birth total. We do this in green. And we do, and you could do this. So X is always before the comma. So the first entry is your X-axis, the second entry is your Y-axis. But your Y-axis doesn't have to be just one entry. So that could be more. And this is where R is getting super easy and super intuitive. So you say, okay, so give me the sum. And now you have the sum. So you just say boys and girls is my Y-axis. That's what I'm now interested in. So if I want to look at plot, this is the sum of boys and girls. So you can be as intuitive. You can. That green is actually terrible. That green is absolutely terrible. It's so dark green. That's nice. Okay. So what else have we asked? So then we can do the proportion of boys of all children. How are we gonna do that? Super easy. You take plot. So here you have all kids, right? All boys, or births. So now the only thing you need to do is to do arbuthnot boys divided by the sum of all. So that's the proportion now. And we're gonna do this dark blue. So that's the proportion between men and women. A male and female birth. Okay, so it's really that easy that you can do arithmetics. You can depict. You can depict your data. Yeah, that's this. So now we can do also the following. We can now. Yeah. So let's do the following. Let's go back to our folder. Let's go on desktop. Let's go to in class BTM600 Module 2. Let's create here a folder labeled output. Let's create that folder, and then we go into that folder and we press Control. And then option. Oh, that doesn't work. Inspector. Oh, yeah. Okay. Right, hold on. Listen to me. Doesn't work right now. Oh, yeah. Okay. So we're clicking now on. So we're creating output. Now we're making a right click on it. That we get, so I'm on a Mac, and I think it should be the same in Windows. So essentially we are creating now, if we're pressing now option, we get copy output as path name. Does that work for everybody? And I want to take this path and create here a write dot folder. Okay. So who's on a Windows computer? If you're on a Windows computer, you have a weirder kind of presentation because you have that instead of this. So this is a so-called backslash. Windows computers are working with backslashes, and you have something like this presentation. You have C:\\. What you unfortunately will need to do, and this is a little laborious, you will need to go, so this is your folder, this is done somewhat desktop. You need to go through this. So make sure that you have everything copied from your path name up until output, including the output. You will also need output. And after the output, please also put this a slash, okay? A slash pointing in that direction. So those of you that are on a Windows computer, you will have a presentation that goes in that way, that has so-called backslashes. You please go into your code of, once you have copied exactly that, so you have write.folder, here the pipe, so smaller sign, hyphen, and your write folder in quotation mark. And now replace all backslashes with slashes. This is important because, and I'm schematically showing this now. So this may look something like this. So this is how it would look like. So you have C:\\, users, and you go and you change everything to a slash. By that, you will be able to access it. So once you have done that, you are basically now writing PDF a PDF of these plots that you're building here. You basically do PDF paste write.folder. Write.folder is your folder here, right? You have created that. It knows that. Write.folder, paste write.folder, and now the file name will be arbuthnot.pdf. SEP equals quotation mark. So now you need to separate each of your plots by a curly bracket. So you will need a curly bracket surrounding each of your plots. Okay. And then you need to close this command by writing device.off, which empowers the graphic engine. So before you run this code, you click your write device off. You see null device and the plot has disappeared. You're closing the graphic device engine, and you do it once again until you see this command. You see cannot shut down device 1 because it's not open. And now you select everything from PDF all the way down to device.off, and you run this thing down. Oh, yeah. You need to obviously put this under quotation mark as well. Sorry, my bad. My bad. Okay, so put this in quotation marks as well, and now run this down. And now when you go on your output folder, you have your graphs as a PDF. And that's pretty cool, right? This is very powerful knowledge, because by that you have created your first PDF graphs.
Professor, do we have to submit that PDF to the Canvas?
Yes.
Okay.
So what not today, on Wednesday next week. And I will change the due date, actually. Let me change the due date. So Wednesday next week. Wednesday next week, December. Okay, that would be fairly late. I guess it's due on September 12th. September 12th, this is September 15th now. Okay. So what needs to be done now is you need to create this code, and I will post this code. And now I will ask you to do this for the CDC data. So for the second portion of this, okay? So you just need to basically repeat the same code, and this is the present data. So this is the data right now from the CDC. Okay. So any questions? Well, if no questions, then that was pretty much all I had for today. So we went through the ArbusNet data. We essentially, it's what you will be asked is the same thing. So we do the max at min for the CDC data. We do some plots, and the plots essentially, the plots will plague you a bit. So I'm anticipating that this will be a little painful for you guys, but it won't be too bad. I'm sure it's going to work out. Make sure that you shut down the engine and that the paste is working well. If the paste doesn't work and you have issues with the paste, just copy paste it. It doesn't have to be the paste function to have it in there. It can be just pasting it in. You can just hard code it. That's perfectly fine. But make sure you're going to have the right address, the right code, and I'm sure it's going to be fun. All right. Well, so I have 5 more minutes. It's like I'm staying on. Please play around a bit with it and let me know if any questions. I'll still stick around. Okay, so this was saved. Nothing's working. Rishabh?
Yeah, yes, Professor. I just want to ask, like,
Okay,
next
good.
week we are meeting in person.
Yes. Wait, no, this is Thursday, right?
Yeah, the next
Isn't
Thursday.
we
next
don't
week
have
is
a class. It's on holiday.
there's no class next week. Yeah, there's a
There's no
holiday.
class next week. It's on holiday for 2 weeks now.
Yes.
Okay.
So we have our next class. Just let me quickly confirm that. The next class is we have our next class on 9/9. This is today, 9/23.
26th.
9/23, and this will
Okay.
23rd. 23rd. This is in
Alright.
14 days from now, and this will be an in-person class. Yes.
All right.
Sure.
Mhm. All right. All right. So I'm gonna be posting a post this practice lab in class. Okay, I will be posting this as an announcement. Okay.
Professor, could you delay the Wednesday submission to a little longer date? Because since I'm new to this and I've just started learning it, I might need a little more time to understand the whole concept.
Okay.
I'd be really thankful.
I will extend the deadline to, let's do 9/22. Take your time with it. Okay.
Sure. Thanks a lot.
Really try to play around with it.
Yeah.
So 9/22. So that's the week after.
Sure.
So that's like 2 weeks
Yeah.
from now. You have time.
Yeah,
Okay.
I'll try to do that properly then. Because I was
Okay.
able to
No,
catch up the initial
but make
program,
sure,
but the lower one was, the plots one was got a little confusing for me.
yes. Please complete Arbuthnot and CDC portion of the assignment. Copy the whole code as ran from the console into a text file and submit the text file and the graphs as PDFs in a zip archive to Canvas. Okay?
Sure. Thanks a lot, Professor.
Of course. Okay, so where's the file? Where's the file? Okay, so I think that should be a nice exercise. Has a good didactic value, and this is going to keep you busy a bit. But it's a good learning curve. It's super important what you're learning, and all of this will be important for the final project as well. Okay, let me know if any questions. If not, all the best. Be in touch and enjoy the break. We're going to see you on the 23rd in person.
Thank you, Professor. Thanks a lot.
Thank you. Take care.
Thank you. Bye-bye.
Bye.